Hello everybody, welcome to my next video, and in this one I want to continue on the topic of my DIY audio DAC. So in the previous two videos I showed you the hardware, how I will approach the project, and in the last video, the part 2, I showed you how I solder up my prototype on the prototyping board when all the components arrived. Then I show you the basic informations about the actual interface, and then talk to you about how I went about writing my full-on library for interfacing with the PCM1792, the DAC chip. So I talked to you about all this file and showed you how I went on to create this library to be fully functional and configurable and not just hard-coded piece of code. And now I have made some progress because I'm also using this project for my school. And before we start the exam weeks, which will be very hard, I would like to show you the progress that I made on this project because I've added a few things and changed a few things. So for the beginning, let's not just dive into the code and let me show you a demonstration video that I prepared for you. Firstly, let's show you the picture of the situation right now. So let me open this one. And as you can see on this picture, you can see that I've added OLED screen over here. So this is an SPI variety of an OLED screen, and I've added it to one of the SPI peripherals on this microcontroller board. I've also added two wires from the USB interface, and these, and I'm gonna show you later, are the actual USB OK wire and the 3.3 volt rail of this interface. So these two can be used to identify if the USB interface card is actually present. Now let me show you a few demonstration videos of the how this display is utilized for now. So in this one, as you can see, that I print some kind of a title page, and on here you can see all the errors that are printed. Right now I'm using the interface, the PCM, and the RTOS. So this is indicating whether these peripherals were initialized correctly. So there are a couple of different errors, so let me show you another video. So in this one, the interface started okay, but the PCM gave a device error. This means that the interface was connected to the USB, therefore the power was present and the interface initialized without problem. But the PCM gave a device error. That's because in this video I didn't connect the power to the DAC card. Therefore the PCM didn't have any power to respond to the SPI commands. There's also an SPI error in order if I maybe botched up the SPI code, so I would know that the SPI was giving error and not the device itself. And then I have another one, and in this one everything should be okay. So the power is going to the PCM card and the interface, and the both are responding well. So this is what I'm going to be showing about. And there's also a demonstration video that I'll be showing you in the next one, and this is when I had a few tests for my display, and I'm gonna create a separate video how this display works and how I managed to write additional code to transform GIFs and other images into code that can be implemented in the microcontroller, so you can see animations like this on the screen. But it's gonna be a separate video because it would be boring just mashing it into this one. So for the differences, let's start with the PCM file. So we were talking all about these files in the previous video, but I made a few changes. The first one are these two functions. So these are the basic functions that interface with the DAC chip. So this one writes into its registers and this one reads from them. And if you recall from the previous videos, these two functions were quite large. They were very long. That's because these two functions handled the SPI communications as well as all the chip select toggling, error catching, and all that. But that was very poorly written because now that I added the display, which is another SPI device, it will be a waste to have two separate libraries that each implement the SPI in their own internal library. So why not have one general purpose SPI library that each SPI device can use, and then at the device library you can call that function and do your own chip select flicking. So let me show what I mean. So I created so-called my low-level SPI.c, and this library handles all the raw SPI communications, so only using the SPI peripheral for sending and receiving data. So no chip select toggling, because that is the responsibility of a particular peripheral functions and libraries, because chip select can vary between the devices. Therefore, if you go back to the PCM, you can see that here is the low-level implementation of the chip select toggling, and the chip select declarations are made in the header file for the particular device. Therefore, the SPI peripheral used and the chip select pins and other peripheral pins are defined in the library that is interfacing for that particular device. Therefore, when we go into the SPI library, it only handles SPI. So this is great, so you can use the same SPI peripheral with the same functions across multiple different devices that use the same peripheral and can utilize the same functions. Therefore, you don't have to copy and paste these functions into every library that uses it, example over here. So how does it work? So let's go into low level, this one. So I have a low level write byte. This just writes 1 byte to the SPI bus. I have a write 2 byte, which could be write register, another name. That's because it sends 2 bytes one after another. So you can imagine this being the device register address and this being the data going into this device address. So it's similar to the HAL implementation. And then I have another SPI write data. This is mainly and only used for the display, and this is when you want to send large amounts of data over the SPI one after another, so you can just input a buffer and then the size of the buffer that you wish to send, and then it's just a for loop that goes through this buffer. And the read byte function, this just reads 1 byte from a particular address of the device register and returns it via this pointer over here. So let me go quickly through this implementation. I'm not going to talk about this too much because this will be a topic for the next low-level video, when we talk about how all these low-level functions work and what all you have to do when you do low-level instead of HAL that does a lot of things for you. So over here I implemented a timeout feature, because in the case that the SPI is not initialized properly or device is not connected or no data is flowing or something is wrong, some of these while functions can get stuck in an infinite loop. Therefore I'm utilizing my timer to actually have a timeout, in this case 10 milliseconds. It's not really a global definition, but in this case it will do. So in case of timeout, it can return an error to the function calling this one. So in this case, I'm transmitting data, and this is one thing that I will mention in the low-level SPI library. You have to wait for the SPI to finish the actual communication, because, well, if you would just send the data, and let's go back to the function that, let's say this one called it, and toggle the chip select back to 1 so that the SPI communication is broken, then the chip would stop the communication, but all the bits might not have been sent. Therefore, you're forcing for this function to actually wait until all the data from the SPI buffer has been sent, and then you can return back and in this case toggle the chip select pin back high. So this is the logic behind this one. Write 2 byte is just like this one, but sending 2 bytes one after another. The write data over here is just, like I said, a for loop that sends multiple bytes, so it's like a special implementation of the 1 and the 2 byte function, and then in the end again waits for the data. And the read byte is reading the last 8 bits. So if you know the first 8 bits, so the first byte that you sent is the address data from which you want to write, and then you have to send another dummy data, so you have complete of 16 clock cycles in the SPI, and the last 8 bits or the last byte of 2 bytes is actually the data that is coming back from the device response. That's why we're receiving dummy data and sending dummy data in between. But other than that, it's the same as with HAL. So this is an overview of how I implemented a separate SPI function, and I'm going to talk about it, as I said, in the future videos in more detail. As you can see, not much in the header file, just the prototypes. So if we go back, as I said, all the particular pin definitions and hardware localization where everything is located is done in the separate file. So as you can see over here, I have the SPI and the chip select declarations, so they can be used by this write register and read register. So this is one way to create a function that can be used locally to all the PCM functionality and not being worried about how the SPI is doing. You just receive the error if it was successful or not, and that's the only thing you're concerned. So from this point on, the SPI is handled and you don't worry about it. So by using these two functions then forward, you're then using all other functions. Okay, as you can see, I implemented a few different errors, so some functions are still void, but some are error status, or in this case PCM error, and this one is again void. So one thing when you're debugging is that you want to catch errors, and in the release you probably don't want to catch those errors because you don't want some wild loops just being implemented. But for the testing purposes, these error functions are very welcome. But I didn't sprinkle them everywhere, and here's the logic behind that. Let's say the init function. So this init function by all logic is the first function that should be called before using this device. Therefore, if the init function fails, the usage of this device doesn't make sense. So you would suggest that if the initialization fails, all the other functions would fail as well. Therefore, there's no point in there telling you, hey, I failed, because I know the initialization function failed as well. Therefore, the initialization function returns its error, and all the functions called after the initialization function, like mute controls and all other controls that will be implemented, start, stop functions, these functions, yeah, they could receive the errors from these upper functions that are inside of them. But if this function that is called after the init function, if this was okay, then you know this will be okay. Because that's like SPI communication just failed in the middle of operation. Maybe it could, so you can restart your device and then you would actually get the init error. So this is a case if the device would fail to work in the middle of operation. You could just reset it and then you should probably catch the error with the init function. That's why I don't have errors everywhere. Now, why did I choose another error type? So this is declared over here in the local PCM file. So that's because the PCM can fail in at least two ways for now, SPI or PCM. So SPI is basically one of the lower initialization errors that can be done in the beginning. So when you're trying to read the device ID and then maybe SPI isn't configured correctly, then the SPI can fail. But if the SPI is working correctly, but the device isn't connected to it, no power connected, then you can get the error PCM. So this is the one that you would trigger if there was no response from it. So if you go back to this function, you can remember that in the beginning, we check if it's alive. So the first thing we do is the read its device ID. So here, if this function fails, that means that the read register function failed. Therefore, that was an SPI kind of error over here. But then if this SPI error didn't occur, therefore the SPI is working, but the device ID was invalid, that means that that was a PCM error. Either the PCM isn't connected, it's broken, or something like that. So here's all the error catching, and I also added them in the struct init function. So you might remember this was a void, but now I have errors over here when I actually write the register. So this is just another test if the SPI is actually working. But again, if this test was fine over here, that means the SPI is working and the device is responding, therefore device should also be working over here. So this error catching over here could be redundant, but I did this in the light as the ST works, because ST also initializes things like that, and the struct init function is the last defense, either the initialization was successful or not. So that's why I have a special PCM error type for differentiating different errors, and other functions that I called after the init don't really need any error catching. If it's for something special, then maybe I'll add that as well. So if we go to the main file right now, so now we went over the PCM changes, now let's go through the main changes. So the first thing that you can see is this list over here. So this is a new structure that I created called new error t. This is temporary name. And this is the actual structure that holds all the initialization errors for all the devices that are currently initialized. So PCM, interface, and the RTOS over here. So in this case, PCM has different errors for SPI and the device itself, therefore it has the PCM error type. The interface also can fail in two ways. For now, let's go to the interface error, to its appropriate header file. It can be okay, but it can also fail as the power is not connected, so this is the first error that should be checked. And the second error is whether the device is actually connected to the USB. So imagine I had multiple USB connections, or you probably did have, where the device had LEDs turned on and everything kind of works, but there was no response for the computer. So it's a dead USB cable, so this is one signal that is present on these boards, usually, that indicates whether the device is actually connected to the USB through the computer. So it can have power, but it doesn't have the connection. So it has two potential errors, therefore I would like to differentiate it between those two, at least for the debugging purposes right now. So if we go back to the new error, so these are the three errors. The RTOS in my case can only fail or succeed. If we go back, so this is all the errors and they're all initialized as particular errors. So if they change, so they go from error state to a non-error state, then we know that this device was initialized successfully. Other than that, the error remains. The first thing we want to do is time init, and I teased it before when I talked about the SPI library that I have a timeout. So let's check a little bit of time, because this is not only for the timeout, but it's for other purposes as well. So first function is of course time init. So this one sets the current timer to 0 and starts the current timer. The timer that I used was in this case timer 5, because timer 5 is 32-bit timer, so you can hold a lot of information for how long it's been running. Let's see this handle. So it's also defined locally in its header file. You can see it's the timer 5. And why I chose the timer 5 and why did I choose it for this particular period? Well, in my case, for my board, the timers are ran on the peripheral clock 1, which runs at 84 MHz. So in order to get this timer to tick at 1 millisecond, the prescaler would have to be 84,000 or 83,999. But that is too much, because the prescaler is only 16-bit, so this value would be out of reach. But a smaller one of 8400 is applicable. Therefore, the timer ticks at 100 microsecond period or 0.1 millisecond tick. And if we calculate it, let's calculate it how long this timer could run at the 32 bits. So it would be 2 to the, let's go to advanced, 2 to the power of 32 divided by, well, 1 millisecond period would have 1 kilohertz frequency, but the 100 microseconds or 0.1 milliseconds is a frequency of 10 kilohertz. So let's divide it by 10 kilohertz. This is this amount of seconds that can be stored in this timer, and then divided by 3600 to get the amount of hours, and then divide this further into 24 to get almost 5 days. So this timer could run without being restarted or flowed over for 5 days, and I think I would run this DAC for 1 day maximum and not just continuously turned on. Therefore 5 days is more than adequate. Now you might think, why am I using a special timer and not like a global variable with an interrupt to increment some kind of global variable for the current millis? And I could use any timer with any kind of prescale to tick at exactly 1 millisecond. Well, that's because in this project I'm using a simple version of RTOS for this school project as well. And the first rule of this simple project is also to not have external interrupts when doing RTOS programming, to create a better deterministic system. So you know that nothing else is gonna interrupt the RTOS routine. Therefore, a timer that is used by HAL or even low level that actually initializes a particular timer in default setting is SysTick, but it could also initialize any other timer that you wish. It creates that timer interrupt. So that interrupt routine just increments a global variable that stores the milliseconds when the timer was started from. And this is unacceptable because I cannot have any interrupts. So the only way I can do it to have a 32-bit timer that has a data register of 32 bits and it counting in the background regardless of operation, and when I want to know the time right now, I can just call one of these functions called timerGetValue to return the value from the timer. And because I have a processor that has such a fast timer, and therefore I cannot have a 1 millisecond pulse for counting, I have to divide the value by 10 to get 1 millisecond value of the timer if I want to have the actual value in milliseconds since the timer was started in the beginning. I also have the delay millisecond function, which basically just takes the current time and adds the milliseconds of delay wished to it, and then waits in this while loop as long as this is larger than the current time. When the current time precedes this value, then it goes out of the while loop, so this is a simple delay implementation. So if we go back to the main, the time init is really the first thing that should be done. The next is the display, because it's the means of communication to the user for any potential errors. Therefore, we call the display init function. This parameter is contrast, and I will show you all about this in the next display video, where I will show you exactly how this library is written, but it's not that relevant for this particular project to talk about only the display for so long. And then I need the GUI, and wait for 1 second. This is just purely cosmetical, so I see how beautiful things flow on the screen. This can be all taken out of the code. No need for any practical use, only for the beauty. And the next thing, I chose to initialize the audio interface, because if the audio interface is not connected or working, what's the point of further operation? Therefore, I initialize the timer is the interface itself, and let's go to its function. So we already saw the header file for this one, which has the interrupt error definition, but it also has its local definitions for the power pin and the USB pin. So these are two input pins that can sense whether the power is on and the USB status is on. But for now, I'm not really sure if my particular version of the USB interface has the USB OK functionality connected to it. Therefore, I'm only firstly checking the USB power. And again, I'm using the timeout, so I'm not just waiting for this pin to get set indefinitely. I'm also giving it a little bit of time. So this is another purpose of timeout. So it's not just reading once, and if nothing is, so if no set pin is present, just continuing it on. So I'm giving it 10 milliseconds to be present at this point. So else it returns a power error, or in the USB case, it would return an USB error. Everything is fine, return OK. So if we go back, so this error is fed into this list for the particular interrupt error. So this is its proper place, it's this one over here. So also if this was not okay, so if the initialization failed, there can be some code implemented in here. Again, if the interface was not successfully initialized, there shouldn't be any point in further initialization, so I could have some display code over here that would print, hey, the display failed. But for my case, I will initialize and try to initialize everything, and then in the end, I will print the status of the actual errors on the screen, so I know what worked and what not worked, so I can actually debug it. So if we just terminate the code, if this one failed, we wouldn't know, well, does the PCM work, or at least RTOS failed? Did maybe the computer failed, or what failed? Therefore, I'm trying to initialize everything, and then in the end, I'm seeing what failed, and then I will deal with it. But right now, I'm just doing the initialization for this project. So let's go to the next one. I have a little bit of error here that I would like to discuss. So the PCM initialization, we already saw that the PCM initialization over here can return the error or the SPI or the device error over here, or even the SPI over here. So it also gets fed its error, whether okay or not, into the list. And if this is not okay, then something should happen. Over here you can see there's the start function. So this is wrong, because here I'm just in the initialization section. So if this fails, I don't want to just start it, because what's the point of starting the DAC if the initialization failed? Also, if this initialization failed, there's no reason for continue with this one, even if this one succeeded, so it's no point into starting up the DAC if the interface failed or the screen failed or anything else. So this start function should really be somewhere lower over here, where everything is initialized correctly. RTOS, the same story, initializing the RTOS. Now you can see that I actually used a parameter for the actual handle for the start functions, and I kept it inside for one reason, and here upstairs is the external definition. That's because this one is actually defined over here, you can see. So this is the actual handler that actually has, let me click on it, all the configuration for this device. So all its registers and the status and connection. And why I decided to keep it and not just have all this function void and just deal with this function internally? Well, one reason for that is that I wanted to have this function a little bit universal as opposed to the screen function, because you might want to have two DACs in the one system. It's not really uncommon to have a dual mono DACs. So each DAC, although it is a stereo DAC, can perform as a mono DAC, and you can have two of those, one for the left and one for the right channel, to create the audio signal. And when using the whole DAC that can be used in stereo but now used in mono, it can have much superior signal to noise ratio and distortion figures. That's just one reason why some people do it this way. And if that was the case, I would create two of these handles and call the initialization twice, and then call the start and stop function for each separate DAC. So then you could differentiate which DAC actually initialized and which didn't. So if there was a particular error, not just a universal function. So this is why, because if you want to have two DACs, then you have a definition over here to insert as many handles for different DACs, and this function could be universal for any DAC. So this is the only reason why, but for my project, when I'll be using only one in stereo mode, this could be all avoided, this function could be void, and would all just go to the common interface over here. So this is one reason why I kept it. And then over here I can start RTOS, and this is dependent on this RTOS macro over here. So this is commented out right now, so currently I'm not using RTOS, but it is working. So all that I do now is start the screen DAC. So this is the function that I haven't completed, and this function would actually start the GUI when the initialization would be successful. So somewhere in here after the init status, so this one would check all the statuses, and this is what you saw in the video before when all the statuses was printed on the screen. That was the doing of this function. So after this would be successful, then this function would be called to empty the screen and actually enter the GUI. So this is the part that I haven't really completed. So actual user interface, when you can change different parameters of the DAC. So this is for the start. So let's go into here and see which settings could I do. The mute settings, where is it? Mute, this could be. These filters over here could be enabled. Maybe digital attenuation if you really want. The actual FMT, so yeah, the actual, let's go down to it, where is defined FMT, so the actual data coming in could be changed. So maybe you have a different USB interface with a different data flow, so you can change it. Let's see, what else could we change? We could change the delta sigma oversampling. Here it is, the mono left and the stereo mode. So this is the actual mode that you would change to mono if you wanted to use two separate DACs for left and right. And in this case, both DACs would be initialized as stereo, but you would actually have to call these init functions with two different parameters to configure each DAC differently. So you would change this to mono. And you would have to also change this one so it knows either it's dealing with left channel data or the right channel data. So the DAC knows if it's the left channel DAC or the right channel DAC. So these are some of the functions. And the DSD, of course. If you were using DSD, you would have to change this on the fly. So let's say you're playing PCM audio data, but then you play some DSD, so the interface would change into the DSD mode. And then you would have to actually change the DSD mode over here, unless there would be just garbage. Now let me show you the documentation for the interface as well. So this is the last thing that I want to show you. So the documentation for these USB interfaces is a bit confusing for me, because there are different manufacturers that perform this. So let's just go into the browser and say USB audio interface. And let's see how many different pictures do we get. Oh, great, just commercial project. USB audio IDVA S. So let's see how this goes. Okay, so this is better. So as you can see, there are many different projects like this one. This one uses XMOS, and this one uses the Atmel processor alongside with an CPLD or an FPGA for reshaping, and this one is really similar to this Monero project. So this one is kind of a benchmark, is a very good project. It handles lots of data, maybe not the best as in performance, but it's very good and used all over the place. It has a good price tag, but it's the only one that I found that has a good data sheet. But as you can see, there are different ones. There's another XMOS device. This one quite popular because there are, I think, 8 core devices that can be used for these purposes, and this company also encourages for this use. But you know what I mean, there's different devices, and there are hardware implementations directly in some project, and there are external ones. They're all these different, but they all, usually when you buy them in this kind of form factor that have a 20-pin header over here, have the same pinout. So in my case, let's zoom in on mine over here. It's a bad picture, come on. Oh, here we go. So it also has this 20-pin connector, and it has 3.3 volts over here, a ground and data, left-right clock, and this is the mute. This is the pin number 1, I think. And this one is the same. If we go down, here is the datasheet. Here's the cable plug, pin 1. And then this pin over here, we saw the 3rd pin is data, clock, left-right clock, and master clock. And if you go back to our picture, it's the 1, 2, 3rd pin is the data, 4th, 5th pin over here. So 1, 2, 3 is the left-right clock, and 6th pin over here is master clock, I can assure you. So the pinout for this part actually matches, at least for the silk screen. But even for this device, you might see that there's not enough information for the silk screen. Therefore, you should read this reference manual for all the other pinout. So you can see this is the cable plugged pin that I was talking about. So it's 1 when the USB cable is plugged. Here's the 3.3 volt pins. So these are not particularly powerful, but it says that can be used to power either an isolator, or it can be used to detect whether the USB is connected to the PC, therefore if this device has power. Here's the DSD on, so when the DSD is coming instead of PCM, this pin is 1, and this should be read by the microcontroller so you can set your DAC appropriately. So when you see that this pin is 1, then you know, oh, I have to change now the mode of the DAC, so it knows it's getting DSD data instead of PCM. And this one can change 0 or 1 depending on the DSD mode, or 64 or 128. And there are lots of other ones like mute 1 when it's changing modes. And oh, that's it. Oh, and this one, I'll probably integrate this one the first time. So these are the first that I'm gonna integrate. So this one, the one that could be very helpful to see on the screen. You might see some DACs that display the sample rate on the screen, and these pins are that. So these 4 pins, let's go down, have like a binary representation of the state, so 0, 1, 1, 1, 1. So this is like a counter, so you can be easily implemented in a truth table. So you can see that depending on the state of these pins, different sample rate is going through here. So this is the actual setting of the sample rate. You configure your computer to send the audio data. So this could be read, so you know what kind of sample rate is going to your DAC, and maybe depending on the sample rate, these filters can be changed. Right now it doesn't say anything over here because this is just for this one, but we know that there are filters that can be changed depending on the sample rate. So this is the oversampling filters inside the DAC. So this is the one thing that you could also consider. So I really hope that this pinout also checks along the other interfaces that maybe you can also buy. They're different from mine. Mine, as you can see, let's go to the picture, is a Bravo IC. So this is the 5th different IC, and there's probably a ton more. But they also all want to choose the same thing. So all serve the same purpose, but they have different implementations IC-wise. Therefore, I really hope that this pinout is functional, and I will report on that in the next video as well when I have my GUI running. So this is all that I wanted to show you for today. So I hopefully see you in a month or less when I finish with all my exams, and then we can continue on this project. So I'll see you then. So thank you for watching, and I'll see you next time. Bye.